Hi everybody. Listen, we're right here in Unit 1. Unit 1 is sort of an overview and an orientation about the subject of differential equations. And today what we're going to do today is just look at some examples. We'll get very quickly to an important computational result, but our main goal right here is to kind of, I don't know, like explore, some themes, like identify some emerging themes that will help you create, a perspective and that will, unify this material for you. Here's another way to say it. We'll create sort of like we're going to work on some computational methods, but we're also going to create a sort of, theoretical scaffolding on which you can hang these computational methods so that by December you're not left with a jumble of material, of computational techniques that simply have to be memorized. So we're going to try to create this perspective today. We're going to start to do that today. Okay, so say for example you might consider the Laplace equation. You might consider the Poisson, this is the Poisson equation. Both of them involve the Laplace operator. You've encountered it before. It's the divergence of the gradient. If you work that out, it's going to be the sum of your second partial derivatives. I know I've got here in this class a couple of students who might be interested in geometry. So let me just mention the following. If you define your Laplacian this way, there are completely invariant ways to define the gradient and the divergence and the gradient so that you can talk about the Laplacian on a Riemannian manifold. We're not going to get into that today, but I just want to mention that because I know I do have students in this class whose interests are in that area. Okay, you can take two different points of view here. You can focus on the equation, or you can focus more on the operator itself. You might consider more generally, you might have an equation, a different differential operator. So you might look at the equation P of u equals 0, it equals f, or P of u equals 0. You can focus on the equation, or you can focus more on the operator itself. And there's a correspondence, right? Solvability properties of the equation can be recast as mapping properties of the operator. So for example, what I mean is to ask whether, think back to your vocabulary, the vocabulary associated to sets, basic vocabulary is associated to sets and relations and functions. You learn this in your undergraduate studies. You remember those words? Excuse me. You remember those words, some of this vocabulary? Injective, surjective, image, and so on. Think about it. To ask whether f is in the image of P is to ask whether the equation is solvable. So you can recast those questions about solvability in terms of mapping properties of the operator. Same thing. You can. How about your regularity properties? If a solution exists, what is its regularity? Is it in C2? Is it in H2? These are all mapping properties of the operator. How many solutions do you have? Remember that? If this has a unique solution, this is a linear operator. If there's only one solution to the homogeneous equation, then your operator is injective. That means if If this has a solution, then it will be unique also. Okay, so your solvability properties of the equation correspond to, or can be recast as, mapping properties of the operator. Whether your operator is linear or nonlinear, well, let me say it like this: the presence of a term like e to the x in a coefficient, that does not cause your equation to be nonlinear. Being linear or nonlinear has to do with the solution, the unknown solution u. Here these are two nonlinear equations. Here you've got a product of u. If products of u and its derivatives occur, then you've got a nonlinear equation. Same thing here. This is the porous medium equation. It models, like say you had a viscous liquid. You can do this at home. Say you have a viscous liquid, like honey, right? And you put it into a cookie cutter, right? And then you lift that cookie cutter, the liquid will spread slowly. The porous medium equation models that physical phenomenon. But you've got u raised to a power, and that makes this equation nonlinear. The predominant behavior of a differential equation or its solution is strongly influenced by the coefficients of the highest order terms. And so the nonlinear equations that we just talked about are organized into a hierarchy depending on how bad the nonlinearity is. Take a look at this is the reaction diffusion equation. The left-hand side is linear. The only if f is nonlinear, like f of u is e to the u or u squared, if f itself is nonlinear, then this equation will be nonlinear. But notice that it's nonlinear only in u. Only in u. Here's your highest order term, which is linear. You've got a nonlinearity in u, in the solution u itself. This equation is called semilinear. But compare it to the minimal surface equation. Minimal surface equation, this equation, suppose you've got a surface that is the graph of an equation lying over a domain in R2, it could be Rn. Okay, a minimal surface, if the surface is minimal, meaning area minimizing, u, the function whose graph is the surface, will satisfy this equation. Okay, so again, the nonlinearity, the hierarchy, the classification depends on how bad the nonlinearity in the highest order terms is. Where do your highest order terms occur in this equation? Here you got the divergence, right? Here's the difference between our online format and in person. If we're in the classroom, well, in person, is better in almost every sense. But if we're in the classroom, then you might resolve to look up the divergence, and maybe by the time you got home you would have forgotten all about it. Right here you can just press a button. If you need to, just press a button and pause the video and look up the divergence. Okay, you back? Divergence is a first order operator. So where do your highest order terms occur in this minimal surface equation? Gradient is also a first order operator. So you got the divergence applied to a quotient. When the divergence hits the gradient, you will generate a Laplace term. Remember, divergence of the gradient is Laplace. But what will be in front of it? Do your quotient rule in front of that. When the divergence hits. Well, this is first order. This is first order. This is first order. You're never going to have anything worse than second order. So where do those second order terms occur? One place they occur is when the divergence hits the gradient and creates a Laplace term. In front of that, you're going to have this, 1 over this term. But this is, so you'll have your Laplace, that's your highest order term, and in front of it will be a coefficient that involves derivatives of u that are strictly lower order. If your highest order term has a coefficient that involves derivatives that are strictly lower order, that equation is quasi-linear. This is a quasi-linear equation. And by the way, just to like anticipate or make contact with some of the material we're going to encounter soon, you don't necessarily want to apply the divergence to this. Leaving it in the so-called divergence form, it's already very well set up for all kinds of techniques that involve integration, because this is perfectly well set up. This is perfectly set up for integration by parts. So you don't even necessarily want to apply the divergence to this. But as I said, for the purpose of classifying what kind of equation this is, you can identify this as a quasi-linear equation. If in your equation there appear products of the highest order terms, then your equation is fully nonlinear. The Monge-Ampere equation is an example. So that's your hierarchy. Semi-linear, where the nonlinearity is in the function u itself. Quasi-linear, where the coefficient of the highest order term involves u and derivatives of u that are strictly lower order than the highest order term. Products of the highest order term mean you are looking at a fully nonlinear equation. Okay. Here's another emerging theme that we're going to, again, use to sort of organize our thoughts as we work our way through the material. The coefficients of the highest order terms are very, very important. Let me give you a really simple example. Using nothing but familiar material from calculus. Suppose you've got an ordinary differential equation, and suppose you've got a solution f. And your equation is such that you are able to derive, this isn't the original equation, but suppose your equation is such that you are able to derive an inequality like this, where a is positive. Then f, even though you don't know what f is, because maybe your equation can't be solved explicitly, but f will be bounded, at least in compact intervals. Let me show you why. And again, this is simple material that you already know. If your equation is such that you are able to derive an inequality like this, then look at the implications of that. Come over here. Now you've got solve this inequality for f prime. It is bounded in absolute value by b over a. Well, I should have said maybe b also positive. Okay, if your derivative is bounded, then, if f is known in even one point, like you might have, think back to your differential equation, ordinary differential equations class in undergraduate studies. In an initial value problem, you would know f in one point. Think of the importance of this. That means that f is bounded, at least in compact intervals. And here's why. If f is known in some point, then f, all the values, have to lie in some band. And here's why. If they didn't, if f went outside of this band, then by the mean value theorem, you would have, at least in some point, you'd have f prime bigger than this bound. So this bound, together with knowing the knowledge of the value of knowing the value of f in even just one point, allows you, at least over compact intervals, to bound f itself. Again, if you went outside of that by the mean value theorem, you'd have a huge derivative somewhere. Even if you were in a non-compact, it's still valuable information. Even if you're in a non-compact interval, at least then f, could go outside of this band, but at least your growth would still be controlled. Okay, this depended. Here I was kind of thinking of a as a constant. A could be a function. So long as it is bounded. So long as it's bounded and non-zero. If A vanishes, then you lose control. You lose information about your derivative. So here's another way to say it. The highest order terms, in some sense, control the behavior of the lower order terms and of U itself. And this is a really simple example using nothing but calculus. It shows how the highest order term controls F. F has to be bounded. Okay, so to lose control of your highest order term, I mean, now I think you can kind of, perceive that to lose control of the highest order term, you lose control of everything. Here's another simple example that you already know from your undergraduate studies. You remember the Euler equations? Remember your Euler equations from an ODE course? These are equations where the coefficient of U and its derivatives can be zero. And when you're interested in solving this equation in an interval, specifically in an interval that includes x equals 0. And you remember these. Here's it's an example of the same kind of thing where the coefficient of your highest order term can vanish. And you remember, I think you remember these, you're specifically interested in solving in an interval that does include x equals 0. And remember what can happen. You can get solutions that involve these powers, x to the 1/2. It's not differentiable at x equals 0. It can be worse than that. You can have powers like x to the minus 1/2. In contrast to this, you get solutions that go to infinity right there in the middle of your interval. Okay, just a moment, please. Okay, so the coefficients of the highest order terms are very important, and we saw that already in an example that involved nothing but calculus. Back here to the PDE situation, you can thinking about that example from calculus, you can intuitively perceive that this kind of coefficient, an equation like this, in a region where x can be 0 is problematic, because there you've lost information about some highest order terms. Likewise, you can probably intuitively perceive that if you're working in a region where x can be unbounded, even though this is not 0, that this equation is also problematic. I'm not asking you to go and look up vocabulary, but just to, kind of anticipate, give a little preview. But not even, not even for that purpose, but really what I want to do is we're trying to identify some emerging themes, and the phenomena that we're observing, they are real. They are real, and they deserve study, so they have their own vocabulary. This equation is what you call degenerate, because your coefficient of a highest order term can vanish. Here, this can't be zero, but it can be as close to zero as you want. There's a name for this too. This equation is elliptic, or it's not an equation because I don't have an equal sign. This operator is elliptic, but it is not uniformly elliptic. Okay, let's layer on one more layer of difficulty. Okay, look at the minimal surface equation. It's similar, except that what appears isn't 1 over x squared. It's not 1 plus x squared, it's 1 plus gradient of the unknown solution squared. This is a coefficient that appears even in a bounded domain. So if you were, back in the previous example, if you're in an unbounded domain, then x can go to infinity, causing this to go to 0. Here, it's even worse, because even in a bounded domain, the gradient of u can go to 0. Sorry, the gradient of u can become unbounded, causing this coefficient to go to 0. How about let me give you another one. This is back to the porous medium equation. The linearization of the porous medium equation, or the porous medium operator. The porous medium equation, the linearization of the porous medium equation contains this. You've got du dt minus gamma u to the gamma minus 1. Now let's just do it in one spatial variable. This could be the Laplace operator in higher dimensions. But your linearization, if you calculate the linearization, your coefficient contains u, and u could vanish. These two problems are harder than this, because you won't be able to answer the question. You won't be able to answer the question whether u can vanish or whether the gradient can become unbounded until you find u. But studying the nature of these coefficients, I mean, if you could find u, you'd be done, right? You were studying the nature of these coefficients in order to find a solution. So it's, it kind of might feel kind of circular to you. Might feel a little bit circular. Okay, the seeming circularity that we mentioned just a moment ago might put you in mind of fixed point theorems, and there are definitely analogs in between our study of PDE and things you've already encountered in your earlier education, all the way back to calculus, which is the first course in the branch of mathematics called analysis. Your main technique was to study a differential equation, sorry, not a differential equation, no, a function, possibly a nonlinear function via its linearization. Same thing here, except that the function is the operator p. Well, let me just mention one thing, a little bit of vocabulary. Why do we use the word operator? It's just, people get really confused about this, even in, an ODE course like 555. P, like P, what I've been calling the differential operator, it is, at the most fundamental level, it is a function. On the most fundamental level of sets, it is a function. But the variable that it takes is itself a function. So very often when we're in that situation where you've got a function that operates on a function, that just gets too confusing. Just traditionally, you call this an operator. But it is, at the most fundamental level, it is a function. Here in partial differential equations, we'll typically be going, even if, like say, like look at here. Maybe you've got your Laplacian in R2 or even R1. So u would be a function of, say, x, y, and t, which is three-dimensional, right? So u might be a function that from a three-dimensional space to R, to the real numbers. But it's u itself that is the variable that p takes. And u is a function that typically lives in some giant infinite dimensional function space. Most of those function spaces that we're going to deal with here in this course, not all, but most of them. So think of, just take them to be so today. Most of them are vector spaces. They may be infinite dimensional, but at least they are vector spaces. So at the most fundamental level of sets, P is a differential operator. That is simply a function that takes an element of this function space and produces an element of this function space. We're dealing first with function spaces that are also vector spaces, and so your linearization, just like in calculus, you linearize at a certain point. Linearize at u, then that will be a map from the whole space F to G. And these are usually normed vector spaces. These are normed vector spaces. Okay, but just like in calculus, so this is what we do in calculus, right? You study the function and solvability properties and mapping properties via its linearization. You remember those two really important theorems, very deep theorems, the inverse and implicit function theorems. They describe solvability properties of f in terms of its linearization, its derivative. And those can always be, the solvability properties of something linear can always be determined completely by the techniques of, that's the power of linear algebra. That's the power of linear algebra. You can always determine them completely. Okay, so just like in calculus, if that linear, we're going to do the same thing. Study P and its solvability properties, its mapping properties via its linearization. Just like in calculus, just as in calculus, if that linearization exists, it is very easy to calculate. I mean, there's just a, and here's how you do it. Here's the recipe. The linearization of P at the point U, at the element U in this function space is, the linearization will itself take elements of that function space and produce elements here in this codomain, another function space. How? You will know that the function dp at u, you will know the function if you know its values. So what is dp evaluated on a function v? It's very simple. You go d, I'm using the notation sigma for a real number because I don't want to use x because that would be a variable in my spatial variable, and I don't want to use t because that's my time or temporal variable. So I'm just going to call it sigma, okay? But it's just a real number. It's just a real number. So take the derivative. you're starting at the point U. You're starting at a point U in the function space, and you're going, which is a vector space. You're starting at the point, here's U, and here's V, right? And you're going on a path. These points in between are U plus, I was going to say T, I'm calling it sigma, because I don't want to use T here. You're going on a path from U into in the direction of V in your giant infinite dimensional function space. But sigma, the variable of that path is just a real number. So now take the derivative with respect to sigma and evaluate at 0. Okay? It's just very simple. I mean, this is a computational if this linearization exists. It's easy to find by this computational device or definition. Okay, let's do it. Let's do it in this example. I'm interested in the reaction diffusion equation. So the reaction diffusion equation would be solved when du dt minus Laplace u equals f of u, right? So I recast this as an operator. This is the operator. And to solve the reaction diffusion equation is to solve P of u equals 0. Okay? But I'm taking the operator point of view, not the equation point of view. There's no equal sign. This is the differential operator P applied to u. Okay, let's find its linearization. You just apply the formula. Just apply the formula. You got P of u. Look at the formula. You're going to first apply, I'll just do it over here. Let me write the formula right here. How do you calculate this? You take a path, okay, that's the recipe. Now let's calculate it for this problem. First, you evaluate P, not at U, but at U plus sigma V. Okay, what is it for my problem? I'm doing the calculational technique. I'm finding the linearization of this differential operator according to the recipe. First, you apply P, not to U, but to U plus sigma V. Okay, what is it in my problem? I've got du dt plus, this is a constant, right? Derivative of a constant times a function is the constant times the derivative of the function, right? Okay? Minus Laplace of u. If you take the Laplacian of u plus sigma v, you're going to get Laplace u minus sigma times Laplace v, right? Again, from calculus, right? Because this is composed of second derivatives. The constant factors out. Now here I've got f applied not to u, but to u plus sigma v. Okay? That's my first step. Evaluate the operator. Evaluate the operator at u plus tv. Okay, look at the recipe. Now what's your second step? Take the derivative with respect to sigma. And I've written it as, let me call your attention to this, it's an ordinary derivative because we're differentiating with respect to the real number, the real variable sigma. Okay? This term, when I differentiate with respect to sigma, there's no sigma here, so its derivative is 0. So step 2. I calculate the derivative with step 2. I calculate the derivative with respect to sigma. Okay, what do I get in my problem? There's no sigma here. The derivative is 0. Right here, what's the derivative of this term with respect to sigma? It's dv dt, right? Okay, there's no sigma here, so the derivative with respect to sigma is 0. I've got Laplace v. Be careful here. You've got a chain rule. This is a chain rule problem. It's the derivative of f. F is real valued, right? It's the derivative of f evaluated at its variable times, this is the chain rule problem, times the derivative of what's inside with respect to sigma. The derivative of what's inside with respect to sigma is v. Okay? Okay, step 3. Step 3 of the recipe. You took your derivative, now evaluate at 0. Okay? So dd sigma evaluated at 0 of p of u plus sigma v is dv dt minus Laplace v, dv dt minus Laplace v. When sigma is 0, you get the derivative of f evaluated at u times v. Okay? This is dp, the linearization of p at u applied to or evaluated on v. Okay? That's how you calculate the linearization of a differential operator. That's always the same procedure. How hard can the computations be? Well, the sky's the limit. If you've got a, really complicated operator, it's harder, but it's the same procedure. Okay, this is the reaction diffusion operator. When you think about it, it models, like a gas or a liquid or something that is undergoing 2 processes, diffusion and a chemical reaction. And you can guess, looking at these, look at this last term, you can guess that there's a difference. When the derivative of u is positive, then that's like the temperature, the reaction the chemical reaction is causing the temperature to increase, which is in competition with the diffusion process, where your heat is, heat tends to spread. You know this from your own, experience. Okay, so there's a difference. When the derivative is positive, you're talking about, a chemical reaction that is that's increasing the temperature, so that's in competition with the diffusion effect. If the derivative is negative, then you've got a chemical reaction that's lowering the temperature, so it's working together with the diffusion process. So you can guess that the sign, that there's an important difference according to the sign. And you can see this. We'll see this even in just the linear case. This part is linear, and if you have du, or I'll use v, still dv dt minus Laplace v, and just say the linear case. You're studying this equation. already in the linear cases, just like what we used our physical intuition for here, there's an important difference according to the sign of C. Okay, we were talking about something a minute ago. I don't remember exactly what we were saying, but oh yeah, okay, I remember. We were talking about, you want to solve this differential equation. In order to solve the equation, you have to analyze those coefficients, but the coefficients involve the unknown solution to the equation you're trying to solve. So, it kind of feels circular, and that circularity might put you in mind of some important theorems and results from calculus and from multivariable undergraduate analysis. It might put you in mind of the inverse and implicit function theorems. They find analogs here. Let's say we're trying to solve this, right? You might try the following. I want to find a u that maps to 0, okay? And I can't find it in one step, but you might try this. You might find some initial guess. We could be in Rn. We could be studying back in multivariable calculus or even one variable calculus, or these could be infinite dimensional. Here in the PDE context, they could be infinite dimensional function spaces. Okay, but nevertheless, it's the same argument here. You might try the following. Okay, I can't solve this all in one step, but maybe I can find an initial. It takes an initial guess, and maybe I can get this close to 0, right? You've seen this all the time. You've seen this, right? Back in calculus, you did Newton's method. Same idea. Okay, so then, now what I'm gonna do is I'm gonna apply my inverse or implicit function theorem. And let's say that, so this point gets mapped to this point, right? It could be f of x1, or p of u1. That's my initial attempt. Okay, now I apply one of those heavy existence theorems, say the inverse function theorem, and I find a neighborhood, right? I study my derivatives. I analyze my linearization, just like we calculated the linearization a moment ago. Okay, and maybe I find that I apply the inverse function theorem, and maybe I find that there's a neighborhood here that gets mapped onto a neighborhood here, and so that every point here is in the image. That is to say that the equation is solvable, but that's not the equation I want to solve. I want to solve the equation here. Okay, so you might try this. Okay, what I'll do is I'll take a point here, close to the edge, and maybe I can find a domain, a point here in the domain that gets sent to here, right? And then I can do the same thing. I'm going to apply the inverse function theorem, and maybe I can find a ball around here. And what I hope to do then iterate, either in a finite number of steps or in an infinite number of steps where I achieve the actual solution only in the limit. But the hope, either way, the hope is that I can kind of chain my way to 0, and then either in some finite number of steps or maybe in some limit process, I have solved my equation. Okay? Well, it's a nice idea. It's a nice idea. Let me show you though, what more realistically, let me show you what can go wrong. You start as before. You're in pretty good shape. But here's what can go wrong. Here's what can go wrong, is that the radii of these balls shrinks, so that you cannot chain your way to zero. Even in the limit, even in the limit, if the radii of these balls is shrinking, then even repeating this iteration process infinitely many times, you may simply be unable to get to zero. Okay, these are some of the issues. These are some of the problems that arise. These are some of the issues that need to be resolved. Let's extract a theme that we're going to be dealing with in this course. These are not just they're not function space, just function spaces. They've got more structure. They are normed function spaces, normed vector spaces. So you've got norms here, and you see from this picture that if you can, well, let's just talk about before I go on, let me just talk about what some of these norms might be. Look, you're trying to solve a differential equation, right? You might be in a space called CK on some domain, or even on a manifold, right? I mentioned, we do have students in this class going into that direction. Okay, so you'll just take the soup of U over the domain, the soup of your, either take each of your first derivatives individually and add them up, or why don't you do it in all one step? If the norm of the gradient is bounded, then doesn't that individually bound each one of the first derivatives? But you'll have so much more luck with this norm instead of doing it individually, because the gradient is, like a physically and geometrically meaningful object. And you might have to go up to, k derivatives. So that's the type of norm. That's the type of norm that you might be using in partial differential equations. So you're really going from one norm vector space to another. Here's another space we're going to see pretty soon. The Sobolev spaces. You might have, instead of k literal derivatives bounded, you might have up u and up to k weak derivatives bounded. You've seen an example already. Remember the minimal surface equation? That was already expressed in what they call divergence form. It's already in perfect. It's already in the perfect form to apply integration by parts. Move the divergence operator off onto another term. When you do that, you can calculate the derivative of things that do not have literal derivatives. We call them weak derivatives. That's another really typical. So these would be replaced by weak derivatives, and that's your Sobolev spaces. Those are two really typical spaces that we're working with. Okay, back to this picture. So say you're working with such a normed vector space, and you've got a choice of norm that is adapted to differential equations and the types of problems that we're going to solve. You can see that the issue here is that you need to maintain uniform bounds. You need to maintain uniform control of the radius of those balls so that they don't shrink. This is a really typical issue. This is really the need for uniform estimates is another one of those emerging themes that we're trying to identify today. It might not be, I'd be very amazed, if this association, sprang to your mind. But you've seen examples of these phenomena in calculus. One of them as early as Calc 1. Maybe I'll leave that for another day. you.